I want you to close your eyes for a second. Imagine you are standing in the middle of a forward operating base. It's night. The air is freezing. Maybe you're in the high Arctic, or maybe the high desert of Afghanistan in winter.
It's desolate.
Exactly. You are completely off the grid, miles and miles from any kind of civilization. You are surrounded by the most advanced military technology on the planet. You have radar systems sweeping the horizon. You have satellite uplinks, streaming terabytes of encrypted data.
Barracks that need to be heated, kitchens that need to run.
Right, a perimeter that needs floodlights. It is a high-tech fortress. But if you listen closely, underneath the wind and the chatter of the radios, you hear a sound.
It's a low, constant, grinding hum.
Exactly. It's
Yeah.
the sound of diesel generators. Dozens of them, chugging away, burning fuel 24 hours a day, 7 days a week. And that sound represents the single biggest vulnerability in modern warfare.
It really, really does. It is the heartbeat of the base, but it's a heartbeat that is dangerously easy to stop because every single drop of fuel that those generators burn has to come from somewhere. It doesn't just, magically appear.
And this is where that whole high-tech image of the military just collides with the gritty reality of logistics. We call this the logistics tail.
Right. And a long logistics tail is basically a giant target painted on your back. It's a vulnerability. To get diesel to a remote base, you have to ship it across oceans, drive it across borders, and then truck it through hostile territory.
It's an immense undertaking. You need drivers. You need armed guards for the drivers. You need air support for the guards.
I mean, the chain of dependencies is just staggering.
I was reading the Defense Science Board report on this, and the costs are.
Yeah.
They're just astronomical.
Yeah.
We aren't just talking about the price at the pump. When you factor in all that security, the transport, the risk, the fully burdened cost of a single gallon of fuel on the front lines can be hundreds of dollars.
Hundreds. And that's just the financial cost, which is the part we can measure easily. The human cost is far, far worse.
Yeah, that was the statistic that really floored me. In the conflicts in Iraq and Afghanistan, something like half of all U.S. casualties were sustained during convoy operations.
Moving fuel and water. It's one of the most dangerous things a soldier can do. Think about that. Not combat patrols, not clearing buildings, driving a truck down a road.
So the problem is crystal clear. The military is addicted to diesel, and that addiction is getting incredibly expensive and unbelievably deadly. But the demand for power isn't going down. It's skyrocketing.
It is. The battlefield of the future is electric. We are talking about directed energy lasers that need these massive, massive pulses of power. We're talking about railguns. We're talking about fleets of autonomous drones that need constant recharging.
You can't run a laser weapon on a diesel generator you bought at Home Depot.
Not a chance. You need a stable, high-density grid, so you have this massive energy gap. You need high-density, reliable power, but you absolutely have to cut the tether to the fuel truck.
That is the paradox.
It's the central problem they're trying to solve.
And that is the setup for today's deep dive. We are looking at a solution that the Department of Defense has been chasing for decades, but it finally looks like they are breaking ground literally. Project Pele officials estimate that a single mobile power source could offset over 1 million gallons of diesel per year.
Just pause on that number for a second. 1 million gallons. That is thousands of truck trips that don't have to happen, thousands of soldiers not exposed to IEDs on the side of the road.
The impact is huge. But here is the hook, and this is really why we're so fascinated by this today. What if you could replace that endless, vulnerable line of fuel trucks with a power source that fits inside 4 standard shipping containers?
Okay.
A source that runs for years without refueling, and here is the kicker that sounds like it's straight out of science fiction, literally cannot melt down.
That is the promise, and that is Project Pele.
Today we are doing a deep dive into what the DoD is calling the TRISO revolution. We are looking at the sources provided by the DoD, the Strategic Capabilities Office, and the Department of Energy to unpack a program that is trying to build a mobile nuclear reactor.
And I want to be really clear right off the top. This isn't just some niche military story. The DoD is explicitly positioning this project as a pathfinder for the entire commercial nuclear industry. This is about rewriting the rule book for how we generate power, anywhere from a battlefield to a disaster zone to the data center that's hosting your cloud storage.
There's a lot of ground to cover. We are going to get into the nitty-gritty science of sub-millimeter particle physics because the fuel itself is the real hero of this story.
It absolutely is.
We're going to talk about silicon carbide coatings, and we're going to find out why on earth the Department of Defense is trucking a nuclear reactor all the way to Idaho.
It is a fascinating story of engineering, of regulation, and of course of military strategy.
So let's start with the project itself. Project Pele. Dr. Jeff Waxman, who's the program manager, had this great quote in one of the press releases. He said, "We are thrilled to move beyond the era of PowerPoint advanced reactors."
That is such a telling statement, isn't it? It's a little bit of a jab at the industry, honestly.
It totally feels like it. I mean, if you follow energy news, you've been hearing about next-gen nuclear for, 20 years? But it's always just these cool renderings, these CGI videos and pitch decks.
Exactly. PowerPoint reactors. Advanced nuclear, what we call Generation IV, has been theoretical for a very, very long time. There have been thousands of papers written, hundreds of conferences held.
And very little concrete poured.
Very little concrete poured. What Waxman is signaling there is a massive shift, a move to actual hardware. They are bending metal. They broke ground at the Idaho National Laboratory on August 19th, 2024. This is not a study anymore. They are building a prototype.
In the form factor, the way it's designed is just wild to me. The main requirement is that the whole system has to be transportable in 4 20-foot ISO shipping containers.
Which is brilliant because it means it utilizes the existing intermodal logistics network. If it fits in a Connex box, it can go on a truck, it can go on a train, and it can go on a ship.
But crucially for the military, it can go by air.
Right. That's the key part. It's designed to be C-17 Globemaster capable. That means you can fly this power plant anywhere in the world in, roughly 24 hours?
So walk me through the deployment.
Yeah.
You fly it in, you land on some rough airstrip, you offload these 4 containers. Then what happens?
You set them up. The sources mention they integrate it with a concrete shield structure at the test site. And that's partly for radiation shielding, but it's also just for physical protection.
Right, from rockets or whatever.
Exactly. But the core idea is rapid integration. You connect the containers. One is the reactor module itself, another is the power conversion system, a third is the control room, and you literally plug it into the base's microgrid.
And then you just flip a switch and you have power. For years.
Essentially, yes. And you have power that doesn't stop, no matter what.
We have to do a little math here, I think, to really understand why the military wants this so badly. We've talked about the problems with diesel, but why nuclear specifically? Why not, a giant field of solar panels or wind turbines?
It all comes down to one thing: energy density. It is simple physics. The energy density of uranium is roughly 2 million times the energy density of diesel fuel.
2
million times.
2 million. There is no chemical reaction, burning gas, burning hydrogen, burning coal, that can even come close to touching the power of the strong nuclear force. So physically, the amount of fuel you need to generate a gigawatt hour of electricity with uranium is microscopic compared to the swimming pools of diesel you'd need for the same output.
Okay, so that's the diesel comparison. What about solar?
Solar is great, but it is diffuse. The energy from the sun is spread out. You need acres and acres of panels to get megawatts of power, and then you need acres of batteries to store it for the night or for a cloudy day.
Not exactly mobile. Not at all. And it doesn't work during a sandstorm, it doesn't work during the Arctic winter, and it doesn't work at night. A reactor gives you that same power and a footprint the size of a couple of parking spaces, and it works 24/7, 365.
That leads to this concept I saw in the sources: unlimited high-speed endurance. That's a phrase they borrowed from the naval propulsion world, right?
It is, yeah. The Navy has been doing this for a very long time. I mean, since the USS Nautilus in the 1950s. If you have a nuclear-powered aircraft carrier, you don't have to slow down to refuel your engines from a tanker. You can steam at full speed indefinitely.
The only limits are food for the crew and jet fuel for the planes.
Exactly. The power plant itself will just keep going. Project Pele is trying to bring that same untethered capability to land-based forces.
To cut the logistical tail completely.
Precisely. If the main power grid goes down, or if your fuel convoys are being attacked, the mission continues. The radar stays on, the lights stay on. The reactor doesn't care about the supply chain once it's there. It just hums along.
And they are actually planning a pilot program for this already at Eielson Air Force Base up in Alaska.
Which makes perfect sense when you think about it. Alaska is a critical strategic location, especially with the Arctic opening up and becoming more contested.
But it's also an energy island.
It is. It's harsh. It's remote. Relying on these long transmission lines that run through hundreds of miles of frozen tundra is a major risk. A single ice storm can knock them out.
So the pilot at Eielson aims to provide, 1 to 20 megawatts of reliable electricity and heat?
Yeah.
But what I found really interesting was the business model. The Air Force isn't planning to operate the reactor. They aren't going to be training 19-year-old airmen to be nuclear physicists.
No, and that's a key distinction from the Cold War era attempts at this, which we can get into later. They are using something called a power purchase agreement, or a PPA.
A PPA. So what does that mean in practice?
It means the military just buys the electrons. They pay a company for the service of having reliable power. The commercial vendor owns the hardware, they operate it, they maintain it, and they bear the operational risk.
So the Air Force is basically just saying, hey, I want to plug in my parking lot that gives me 5 megawatts, 20 and 47, and I don't want to know how the sausage is made.
Essentially, yes. And that's a huge deal because it shifts the operational burden to private industry, which in turn helps stimulate that commercial market we talked about. It creates demand.
Okay, let's get into the sausage, though, because that's really what we're here for, the fuel. The sources keep using this term, TRISO, T-R-I-S-O.
Tristructural isotropic particles.
And they keep calling it a paradigm shift. Now, I want to pause here. When I picture nuclear fuel, I think of The Simpsons. I think of a glowing green rod, or maybe one of those long metal tubes they use in big power plants.
Right, fuel rods. That's the traditional image. Bundles of these long zirconium alloy tubes filled with little ceramic uranium pellets, all sitting in a giant pool of water. TRISO is a completely different beast.
So what does it look like if I hold it in my hand?
If you held it in your hand, it would look like coarse black sand. Or poppy seeds?
Poppy seeds.
Yeah.
Seriously.
Seriously. Tiny sub-millimeter spheres. Less than a millimeter in diameter. You could hold thousands and thousands of them in your cupped hands.
So the fuel isn't a solid rod. It's a pile of sand.
Well, they take those individual particles and they compact them. In the case of Project Pele, the slides show they're compacting them into these little cylindrical fuel pellets, roughly the size of your finger joint, about 12 millimeter by 25 millimeter.
Okay, so they're making little pellets out of the sand.
Exactly. Sometimes they make them into spheres the size of billiard balls for other reactor designs. But the magic, the real innovation, isn't in the shape of the pellet. The magic is inside each individual grain of sand.
Okay, so let's zoom in. If I have a super-powered microscope and I slice one of these tiny poppy seeds in half, what am I looking at?
You're looking at a masterpiece of material science. It's like a tiny, perfectly engineered jawbreaker candy with very, very specific layers.
All right, let's break it down layer by layer.
Okay. In the absolute center, you have the fuel kernel. That's your uranium oxycarbide or uranium dioxide. That's where the fission happens. That's the engine. It's tiny, maybe 500 microns across, half a millimeter.
Okay, so the hot stuff, the radioactive part, is right in the middle.
Right. Now, surrounding that is the first layer, the porous carbon buffer. Think of this layer as a sponge.
A sponge.
Yeah.
Inside, what's supposed to be a solid rock?
A microscopic sponge, yeah. See, when a uranium atom splits, it doesn't just create heat, it creates fission products. And a lot of those are gases, like krypton and xenon.
Okay.
Now, if you trapped those gases in a totally rigid shell, the pressure would build up and build up as they expand, and eventually the shell would crack. The buffer layer gives those gases a place to go. It has empty space, so it absorbs that expansion.
That's smart. It's like a shock absorber for gas pressure.
That's a perfect analogy, exactly. Then, outside of that, you have a layer of inner pyrolytic carbon. It's another dense structural layer. But the real star of the show, the layer that changes everything, is the next one. Layer number 3, silicon carbide.
The sources call this the paradigm shift. So why is this one layer so special?
Well, silicon carbide is one of the hardest materials known to man. It's a ceramic. It's used in the ceramic brake discs on high-end sports cars because it can handle insane temperatures and friction.
I think they use it in some types of body armor too, right?
They do. It's used in bulletproof vests. In this fuel particle, that layer of silicon carbide acts as a miniature pressure vessel. It creates an impermeable, incredibly strong seal around that tiny kernel of uranium.
So, wait. Instead of building a giant concrete dome and a massive steel vessel to keep all the radiation in, you are wrapping every single one of these billions of atom-splitting particles in its own tiny bulletproof containment dome.
That is the perfect analogy. The fuel is the containment. Each particle contains itself.
And there's one more layer, right? The final one.
Right, the outer pyrolytic carbon. And that layer basically just protects the silicon carbide layer and helps bond all the individual particles together when they're pressed into those pellets we mentioned earlier.
So why does this matter so much?
Yeah.
I mean, why go to all the trouble of making billions and billions of these tiny, perfect jawbreakers?
It's all about heat. In a traditional reactor, the big ones, if you lose your coolant, if the water drains out or the pumps stop, the fuel gets so hot that it melts the metal cladding that's holding it.
Yeah, it's a meltdown.
That's a meltdown.
Hmm.
The fuel turns into this liquid sludge, corium, and it can release huge amounts of radiation. That's the Fukushima scenario.
Right.
But silicon carbide has an incredibly high melting point. We are talking about it being structurally stable at temperatures over 1600 degrees Celsius. The physics of the Pele reactor are specifically designed so that even if you lose all cooling, the temperature naturally stabilizes below the melting point of that coating.
So you're saying it physically cannot get hot enough to melt its own containment shell?
Correct. The reactor can't produce enough heat to destroy the fuel. The fuel remains solid. The fission products, all the bad stuff, stay locked inside those little glass-like beads.
That's a fundamental shift in safety. But that brings up the kinetic question. This is a military project after all. We're talking about putting these things in shipping containers near a potential battlefield.
Right.
What if someone shoots it? What if a truck carrying it flips over?
And that is a primary top-of-mind concern for the DoD, and that is where the rugged nature of TRISO really comes into play. The sources explicitly mention kinetic destruction resistant.
Kinetic destruction. That's a very polite way of saying getting blown up.
It is, but let's think about the Navy again for a second. Naval reactors are designed to withstand 50 G shock loads. That is 50 times the force of gravity. Commercial earthquake standards are maybe 5 Gs. The Navy builds things to take a direct hit from a torpedo and keep running.
So that level of toughness is already part of the military nuclear culture.
Exactly. And TRISO takes that robustness and shrinks it down to the microscopic level. So even if, in a worst-case scenario, a missile hits the container and breaches the steel reactor vessel, the fuel pellets themselves, those little compacts of poppy seeds, are incredibly hard to break.
They don't just shatter into dust.
Right, and even if you could break them apart, the individual particles are still incredibly tough. You might make a mess locally, but you aren't creating a radioactive cloud that drifts over a city. It's a fundamentally different failure mode.
There's also the proliferation angle to consider. The sources mention it uses HALEU fuel. That stands for high-assay, low-enriched uranium.
That's a bit of a mouthful, but it's a really important detail. Naval submarine fuel is very highly enriched. It's effectively weapons grade. You could, theoretically, make a bomb out of it if you knew how.
But HALEU is different.
HALEU is enriched to less than 20%. That's well below the threshold for what's considered usable for a nuclear weapon.
And because that uranium is locked inside these billions of tiny silicon carbide shells, it must be really, really hard to get it out to try and enrich it further.
Exactly. It's incredibly difficult to process chemically. So as a target for theft or for someone trying to make a dirty bomb, it is a very, very unattractive option compared to other radiological sources.
Okay, so we've established that the fuel is tough as nails, it's hard to weaponize. But let's go back to that phrase, meltdown-proof. The host in me absolutely loves that headline. The cynic in me asks, is that just good marketing, or is it actual physics?
It is a bold claim, for sure, but in this specific context, it is based on physics, not marketing. In the nuclear industry, we prefer the term inherently safe.
Inherently safe. Unpack that for us. What's the difference?
A traditional light water reactor, the big concrete domes you see along the highway, is engineered safe. That means it relies on active systems to stay safe. Pumps must pump water. Valves must open. Computers must tell the control rods to drop in an emergency.
You have to actively fight a meltdown.
Yes. If those active systems fail, if you lose power to the pumps, like at Fukushima, the physics of the core actually works against you. The heat continues to rise until things start to melt. It's like balancing a broom on your hand. You have to constantly make adjustments. If you stop paying attention, it falls.
Okay, so that's engineered safe was inherently safe.
With TRISO and these gas-cooled microreactors, the safety is inherent to the materials and the physics. As the fuel gets hotter, the nuclear reaction naturally slows down. There's a phenomenon called Doppler broadening.
Doppler broadening. Sounds complicated.
Without getting too deep into the physics weeds, as the uranium atoms heat up, they start to vibrate more. This vibration makes them wider targets for neutrons, but in a way that makes them absorb the neutrons without splitting. They essentially start to eat the fuel for the reaction without producing more energy.
So the hotter it gets, the less efficient it becomes. It naturally chokes itself off.
Exactly. It's a negative feedback loop built into the physics. And because the fuel itself can withstand such incredibly high temperatures without melting, you have this massive, massive safety margin.
The sources kept mentioning walkaway safety.
That is the gold standard in reactor design.
What does it mean literally?
It means the operators can literally stand up, walk out of the control room, turn off all the lights, and cut all external power to the facility. The reactor will just sit there, get hot for a while, its own physics will cause it to settle down, and then it will just passively cool off by radiating heat into the air. No meltdown, no explosion, no human intervention required.
That completely changes the safety equation. And it must change the design of the entire plant,
It
doesn't it?
absolutely does. It changes the entire barrier philosophy.
We saw that comparison in the Navy sources.
Right.
Traditional nuclear defense relies on 4 barriers.
Right. In a submarine, for instance, you have the fuel matrix itself, then the welded primary system, which is all the pipes, then the sealed reactor compartment, and finally the ship's hull. In a commercial power plant, you have the fuel cladding, the reactor vessel, and that giant concrete containment building.
And all those external barriers are massive and expensive because the first barrier, the fuel cladding, is actually relatively weak.
Precisely. But with TRISO, the first barrier, that tiny particle coating, is by far the strongest one.
So if your first line of defense is nearly unbreakable, you don't need all the massive, expensive steel and concrete structures on the outside.
Exactly. And that is what allows you to shrink the whole thing down to the size of a shipping container. You are fundamentally trading brute force concrete for elegant chemistry and material science.
This has to bring us to the regulators. The Nuclear Regulatory Commission, the NRC, I picture them as, very careful, very slow-moving, and very used to checking boxes for giant concrete domes cooled by water.
That's a fair characterization. And historically, the NRC has only really known how to license one type of reactor, the light water reactor. That is what they have 60 years of data on. That is what all their regulations are written for. Their computer codes are literally designed to simulate water cooling.
So how on earth do you license a mobile shipping container reactor that runs on poppy seeds and uses helium gas for cooling?
That is the billion-dollar question for the entire advanced nuclear industry, and that is why Project Pele is so critically important. The DoD is acting as a pathfinder.
A pathfinder.
They are essentially running interference for the commercial world. The NRC is working directly with the DoD and the Department of Energy on this project. They are observing the testing, they are reviewing the safety analysis, they are figuring out how to certify the transportation packages.
The sources mentioned they're working on certifying the package for highway transport. That seems huge. Driving a nuclear reactor down the interstate.
It is unprecedented for this type of deployable reactor. We ship used fuel in these massive, heavily guarded casks occasionally, but shipping a brand new, ready-to-go reactor core is new territory. If the DoD and the NRC can agree on the safety case for this, if they can prove that those TRISO particles are so robust that they're safe enough to be on a truck sharing the road with everyday traffic, that sets a crucial precedent.
And that precedent opens the door for commercial companies to follow later.
Exactly. It creates a regulatory pathway that simply didn't exist before. It saves the commercial industry years of time and hundreds of millions of dollars in legal and analytical fees.
Now, I want to take a step back into history for a minute, because when I was reading through the background material on this, I found something that really surprised me. This isn't the first time the U.S. Army has tried to build mobile nuclear power plants.
No, it is not. There is a ghost in the room, and its name is the Army Nuclear Power Program.
From 1954 to 1977.
A really fascinating era of nuclear history. They actually built and operated 8 different reactors.
I saw the list. The SM-1 at Fort Belvoir, the ML-1, the PM-1 at Sundance Air Force Station in Wyoming. They even had one on a barge in the Panama Canal, right? The Sturgis.
They did. The MH-1A, it was built into the hull of a World War II Liberty ship. It powered the canal locks for several years during a drought when the hydro dams were low.
So we had mobile and transportable nuclear power in the 1960s. Why don't we have it now? What happened to that program?
It really came down to complexity and cost. The ML-1, for example, stood for Mobile Low Power Reactor. It was designed to be towed by trucks and set up in the field. But the technology back then, they were basically trying to shrink down a conventional, complex reactor design.
It was like the movie Honey, I Shrunk the Nuclear Plant.
Pretty much. And it turns out when you shrink a really complex system that's full of high-pressure pipes, pumps, and valves, it becomes an absolute nightmare to maintain. They were unreliable, they broke down a lot.
And they required huge crews, right?
Massive crews of highly trained specialists. So you might be saving diesel fuel, but now you're having to fly in a team of PhDs to keep the thing running. The logistics problem just changed shape. It didn't disappear.
And the fuel technology wasn't there yet.
Not even close. They didn't have TRISO. They had these metal plates or pins that were much more fragile. A meltdown was a genuine risk that you had to constantly, actively manage with all those complex safety systems.
So at the end of the day, the juice wasn't worth the squeeze.
Correct. Diesel was cheap, the reactors were expensive and finicky, so the program was canceled in 1977.
So why is this time different? Why isn't Project Pele going to end up in the scrap heap of history like the ML1 did?
I'd say there are two main reasons. The fuel, which we've talked a lot about, and the power of modern computer modeling.
Okay, so the fuel first.
As we discussed, TRISO completely changes the safety game, which in turn radically simplifies the machine. You don't need all those redundant active safety systems with pumps and backup generators. That makes the reactor simpler, lighter, and more reliable from the get-go.
In the modeling.
We have spent the last 20-plus years simulating these advanced reactors. The Department of Energy's Advanced Gas Reactor Program, the AGR program, has been basically putting TRISO fuel through torture chambers at Idaho National Lab. They've been heating it up, crushing it, exposing it to intense radiation for years at a time. We have mountains of data now that says, yes, this works, before we even build the final unit.
So that quote about getting beyond PowerPoint is true, but it's building on 2 decades of digital work.
Right. We are building with a very high degree of confidence because of those decades of research and simulation. The 1960s engineers were working with slide rules, were working with supercomputers.
It also seems like it's not just the Army acting alone this time. The whole ecosystem around the project seems much larger and more robust.
It's a whole-of-government approach. That's the official term they use, and it's very accurate.
So who all is at the table?
Well, you have the Strategic Capabilities Office, or SDO, leading the charge for the DoD. You have the Department of Energy and Idaho National Lab doing the heavy lifting on the physics and the testing. You have the NRC, of course, on the regulatory side. And interestingly, you have NASA.
NASA. Why is NASA involved in a military reactor project?
NASA needs nuclear power for space exploration, for deep space probes, for potential moon bases, for Mars missions. Solar panels don't work very well on Mars during a global dust storm, and they don't work at all past Jupiter. So NASA needs small, reliable, super tough nuclear reactors. They are partnering on the TRISO production facility because they need the same fuel.
That makes perfect sense. If you can make a reactor safe enough and tough enough to launch on top of a rocket, which vibrates violently, it's probably safe enough to drive down a highway on a truck.
Exactly. And then, of course, you have the industry partners. BWXT is designing and building the reactor. You have Northrop Grumman, Rolls-Royce, Torch Technologies all involved. These are the heavy hitters of the defense and engineering world.
Rolls-Royce makes nuclear reactors. I always just think of the fancy cars.
That's a common misconception. The car company was split off decades ago. The engineering firm Rolls-Royce is a giant in aerospace and defense power. They've been building the reactors for the UK's nuclear submarine program for decades. They know what they're doing.
So this whole-of-government approach is designed to do more than just build one prototype. It's designed to restart the entire supply chain.
Yes, that's a huge part of it. The U.S. lost a lot of its nuclear manufacturing capability after the 1980s. We just stopped building new plants. This project is pumping money and, more importantly, consistent demand into the system to get companies to start making the fuel again, making the specialized graphite, making the high-temperature steel.
Let's talk more about that commercial spin-off. We touched on it, but the sources make a really specific and powerful historical comparison to Admiral Rickover and the USS Nautilus.
It is the perfect parallel. In the 1950s, a brilliant and famously cantankerous admiral named Hyman Rickover decided the Navy absolutely needed a nuclear submarine. He willed it into existence. He forced the development of the pressurized water reactor, or PWR. The USS Nautilus launched in 1954, and it changed naval warfare forever.
And that PWR technology didn't stay locked away in the submarine fleet.
Not at all. Just 3 years later, in 1957, the Shippingport Atomic Power Station went online in Pennsylvania. It was the first commercial nuclear plant in the United States. And what was it? It was basically a carrier reactor sitting on land. The design was nearly identical.
So the entire commercial nuclear industry that we see today, all those big concrete domes, are the direct descendants of the nuclear navy.
Correct. They are light water reactors because the Navy needed light water reactors for its submarines. Now, fast forward to today and look at Project Pele. The DoD needs a mobile, gas-cooled, TRISO-fueled reactor.
So if Project Pele works, the shipping port of the 2030s will be
a commercial microreactor. Maybe it's powering a Microsoft data center or a remote mine in Canada or a hospital in a city. The prediction, the hope, is that Project Pele will do for advanced nuclear for Generation the Fifth what the Nautilus did for Generation 2.
It effectively de-risks the whole proposition. It subsidizes the R&D, and crucially, it subsidizes the regulatory pain.
Exactly. Private companies hate regulatory risk more than anything. If the DoD pays to clear that path with the NRC, commercial money will flood in right behind them.
Let's look at the actual rollout plan. The timeline in the slides it's really aggressive.
Very aggressive for the nuclear world. The design competition was from 2020 to 2022. Fabrication started in late 2022. They are assembling the prototype at Idaho National Lab right now in mid-2024.
And when do they expect to actually produce power?
The target is for late 2024 or early 2025. Then they want to move it to its operational placement in that concrete shield setup we talked about by 2026.
That is just lightning fast for a nuclear project.
It is. And at INL, they're not just going to turn it on and see if it works. They are connecting it to a specialized microgrid that can simulate real-world battlefield loads. They'll be able to simulate a laser weapon firing, which draws a massive pulse of power, or a huge radar array powering up to see if the reactor can handle those sudden spikes and drops in demand.
They're really putting it through its paces.
Absolutely.
Now, we have to address the elephant in the room. We can't have a long conversation about nuclear power without talking about the waste. What happens when the fuel runs out after a few years?
This is a major concern for any nuclear deployment, but especially for a military one. You absolutely do not want to leave radioactive waste on a battlefield or in a foreign host country.
The sources outline what they call a sealed core concept.
Right. And this is another key difference from big commercial plants. In a big plant, you have to shut down every 18 months or so. You open the top of the reactor, and you painstakingly shuffle fuel rods around in a deep pool of water. It's a complex operation.
But these microreactors are designed more like a battery.
Exactly like a battery. You fuel it once at the factory. You seal it up. You ship it to the site. It runs for, say, 3 to 5 years, maybe longer in future designs.
And when it's done? When the fuel is spent?
You don't refuel it there. You unplug it, you put it back on the truck or the C-17 plane, and you ship the entire sealed reactor unit back to the manufacturer or to a central federal repository.
So the user, the soldier on the base, never touches the fuel, ever.
Never. The waste just leaves with the unit. The problem is returned to the experts.
But where does it go eventually? The sources pointed to the Navy's long experience with this exact problem.
And this is really reassuring data that most people don't know about. The Navy has been disposing of entire nuclear reactor compartments for decades. When a submarine is retired, they literally cut the reactor section right out of the hull.
I saw the pictures in the source material. There are these huge sealed steel cylinders.
They are. They put them on a barge. They take them up the Columbia River to the Hanford site in Washington State. They put them in a big, dry trench, and they bury them.
That's it. They just bury them. Sounds almost too simple.
It sounds simple, but it's incredibly effective. The reactor compartment itself is such a robust container, and the most radioactive fuel has been removed. The remaining activated metal is safely contained. Environmental studies have shown that the lead shielding and the steel will safely contain the radiation for thousands of years, far longer than it remains dangerous.
And with TRISO, the fuel itself effectively is its own disposal cask.
Exactly. Because those fission products are chemically and physically locked inside those silicon carbide beads, the disposal profile is potentially much, much simpler than dealing with traditional used fuel rods. You are disposing of a sealed, solid block of material that is incredibly stable and resistant to leaching into the groundwater.
So we have the tech, we have the history, we have the regulatory path, and we have a plan. Let's speculate a bit on the future here. The micro-future, as they call it.
This is where it gets really exciting. The Defense Science Board report explicitly mentions disaster relief as a prime use case. Imagine a massive hurricane hits Puerto Rico or New Orleans. The entire grid is destroyed. It takes months, even years, to rebuild the towers and lines.
And today, we send in thousands of diesel generators. And then we have the problem of getting diesel ships into the ruined ports and diesel trucks down blocked roads.
Right. It's a logistics nightmare on top of a humanitarian crisis. But now, imagine a C-17 lands at the airport. It offloads 4 containers, you truck them to a stable location. Within days, you have 5 megawatts of clean, reliable power.
That's enough to run the main hospital, the water purification plants, the emergency command centers.
And you don't need a single drop of fuel for the next 5 years. It's a pop-up, resilient grid.
And I can't help but think about data centers. AI is driving energy demand through the roof. Tech companies are getting desperate for carbon-free 2047 power to run their server farms.
They are, and they don't want to sign up to build a 10-year, $10 billion traditional nuclear plant. They want to buy a module, drop it in the parking lot next to the data center, and turn on the servers. Project Pele is proving that form factor is not just possible, but practical.
It's just fascinating to think that the solution to greening the grid might come from a green, camouflage-painted shipping container.
The irony is pretty thick, yeah.
So to wrap this all up, let's just recap the big breakthroughs here. What are the key pillars?
I really see three of them. First, and most important, is the fuel. TRISO and its silicon carbide coating. That is the physics-based safety net that makes everything else possible.
It's the innovation that allows for walkaway safety. No active cooling needed. Meltdown-proof, in effect.
Second is mobility, breaking the diesel logistics chain. It's about turning energy from a consumable liquid that you constantly have to ship into a durable, deployable asset that you ship once.
And the third pillar?
Regulation. The DoD acting as the icebreaker, clearing a path through the frozen sea of NRC regulations, and creating a safe channel for the commercial industry to follow.
It really is a remarkable convergence of technology, strategy, and necessity. We usually think of nuclear power as these massive, scary, stationary monuments to 20th century engineering. They're like pyramids, giant, immovable, and kind of foreboding.
That's a very fair image for most people.
But with TRISO, with Project Pele, nuclear is becoming something else entirely. It's becoming a product. It's becoming like a battery. Portable, sealed, and inherently safe.
The nuclear battery concept is the perfect way to frame it.
And here is the thought I want to leave everyone with. If the Department of Defense succeeds in parking your reactor at Eielson Air Force Base, if they can land it, plug it in, and basically ignore it for years while it powers a critical national security mission, how long until that technology comes home? How long until there is a nuclear battery powering the data center that hosts your emails? Or the hospital down the street, or maybe even the neighborhood you live in?
The age of artisanal, one-off, custom-built nuclear plants is ending.
And the age of mass-produced, factory-built nuclear batteries is just beginning. Thanks for diving in with us.
It was a real pleasure.
We'll see you next time on The Deep Dive.